So this lecture is a continuation of the last lecture, so I will start it without much preamble. So in the last lecture, the takeaway from the last lecture is that the neutral axis for bidirectional bending of any arbitrary cross section passes through the centroid of the cross section. So let me just write it down. So neutral axis of any arbitrary cross section under bidirectional bending passes through the center. Okay, so I have drawn the neutral axis, the green color line, through the centroid. I have taken the elemental area dA, which is at a perpendicular distance zeta from the neutral axis, and the coordinate of the elemental area dA is x and y. Now let us assume alpha is the angle made by the neutral axis with the horizontal axis x. Okay, we don't know yet what alpha is, and we will figure out later in this lecture what is the value of alpha and which parameters do the alpha value depend on. Okay, now let me draw the moments. The applied moments are mx, as we have done in the last lecture, and my. These are both positive moments acting about the x and y axis. Now let us go ahead and see what is the expression for sigma z. So the objective of this lecture is to derive the expression of sigma z, that is the normal stress at a point on the cross section, in terms of the applied moments and the sectional properties. So now from geometry we can see that zeta, which is the perpendicular distance of the elemental area from the neutral axis, can actually be written as x sine alpha plus y cos alpha. Okay, so you can easily see this from the geometry. You can easily derive this expression from the geometry. So if this is zeta, then sigma z at dA is nothing but E by R into zeta, okay, which is going to be E by R into x sine alpha right. So if this is the value of sigma z, or normal stress at dA, then the bending moment mx, what would be the expression of bending moment mx in terms of sigma z? Okay, so what is happening? Let us try to understand the physics. The applied moment mx as well as my is going to be resisted by the internal stresses that is developed in the cross section. The only internal stress that is developing in the cross section is sigma z, right, in the z direction. So this sigma z is going to balance or equilibrate the externally applied force, which is mx and my in this case. So in the previous lecture we have seen that the resultant normal force or axial force because of sigma z is equal to 0, right? And now let us see how are we going to relate mx and my in terms of sigma z. So let us first go ahead with mx. Now mx can be written, just imagine what is, just Try to figure out what is mx. Mx is sigma z into dA, which is the force on the elemental area dA because of the normal stress sigma z. Okay, so it is going to be sigma z into dA is the expression for the force, elemental force, and that into y is going to give me the value of mx, right? So integrated over the area. So let me write this in a better form. So it is going to be sigma z y into d. In place of sigma z, I can write E by R integral of x sine alpha plus y cos alpha into y into dA. Now what is that equal to? That is equal to E by R integral of xy sine alpha dA plus y square cos alpha dA. Now how can I write this? I can write this as E by R sine alpha into xy dA plus E by R cos alpha y square d. Now let us look into this more carefully. So what is this equal to? This is equal to Ixy, which is the product moment of inertia. And what is this? This is equal to Ixx for the given section. Now sine alpha and cos alpha could be taken outside the integration because they are not a function of xy coordinate. Okay, so I could easily take them outside the integral, and therefore this could finally be written as E by R Ixy sine alpha plus Ixx cos alpha. Okay, so this is the expression for mx. Let me mark this. Okay, so this is going to be the expression for mx, right, in terms of the sectional property and alpha. Now let me see how can I write the expression for my. So my can be written exactly similar to mx. My is sigma z dA is the elemental force over the area dA into x, right? As simple as that. So that can again be written by E by R x sine alpha plus y cos alpha into x into dA. So that I will skip the in between steps, and that can be written as x. Okay, let me write this: x square sine alpha plus xy cos alpha into d. That can be written as E by R. E by R Iyy sine alpha plus Ixy cos alpha, right, and that is going to be equal to my my. Right, so I have been successful in writing mx and my in terms of my sectional property Ixx, Iyy, xy, and sine alpha, cos alpha, Young's modulus, and the radius of curvature. Now out of this, I yet don't know what is alpha, I yet don't know what is r. So let me try to express this in a better way. So the previous two equations of mx and my therefore can be written in matrix form as mx my is going to be E by R it is going to be Ixy, Iyy, Ixx plus Ixy into sine alpha cos alpha. Okay, so this is going to be sine alpha cos alpha. Now let us see what is happening to the equation. So in this equation the unknown part is this and this. So these are unknowns. Okay, this is the known parameter. Of course, right? I always have to know the applied moment. Otherwise, that's not possible, right? So I always know mx and my. So let us try to express E by R sine alpha cos alpha in terms of the known parameter. So that would be easy, right? So once I have this matrix expression, that should be just the inverse of this matrix. Just the inverse of this matrix into mx my. Okay, as simple as that. So I can express the unknown on the left hand side to the known parameters. So if I find out the inverse of this, the inverse is going to look something like this. Let me just write it down. You can very well find it out yourself just as a check, that it is Ixx Iyy minus Ixy square, and that is minus Ixy and Ixx Iyy and minus Ixy, and that into mx my. Okay, and right, so what is now happening? I'm expressing E by R and sine alpha cos alpha in terms of my known parameter, that is the applied moment and the sectional property. So this is a important step done. Now what do I do? Now I know that sigma z is nothing but E by R x sine alpha plus y cos alpha. Okay, I know sine alpha cos alpha. Okay, I very well know that. So then I can always plug this in here and write my sigma z in terms of the known parameters, that are the sectional property and the applied moment. So if I do that, then sigma z ends up being myixx minus mxixy by ixx iyy minus ixy square into x plus, I'm skipping the intermediate steps, you can always do that for yourself, and then I have mx iyy minus my ixy. I can always do a mistake here, so it's better that you do the derivation and check for yourself that these expressions are correct. So into y. Okay, so this is the value of sigma z. Now I know sigma z in terms of all the known parameters. So I can find at any point given by, defined by x and y coordinate on the section, I can find out the normal stress at that point, provided I know the applied moment and the sectional property. Okay, I can even rearrange this if you want to and write it as mx iyy into y minus ixy into x by ixx iyy minus ixy square plus mx into ixx into x minus ixy into y by ixx iyy minus ixy square. Okay, so this sigma z, this 2 is the equation or expression that I wanted. Okay, these 2 are the equations that I wanted. Okay, I mean this is just a rearrangement of this, right? I mean nothing more than that. So now I know this. Another thing that I know from whatever I have derived is that tan alpha is going to be equal to my ixx minus mx iyy by mx iyy minus my ixy. Okay, so where alpha is the angle between neutral axis and x-axis. Okay, now one thing that has to be observed here. So we see that the angle that the neutral axis makes with the x-axis, that is the orientation of the neutral axis, depend on the values of mx and my, apart from the sectional properties ixx, iyy and ixy. So apart from the sectional property, cross-sectional property, the tan alpha also depends on the relative value of the applied moment mx and my. This is very counterintuitive. See, all this while when we were dealing with unidirectional bending, we always thought that the neutral axis just depend on the property of the cross section. But now we see for bidirectional bending, the orientation of the neutral axis is always going to pass through the centroid, that's for sure, whatever be the applied force. Okay, but the orientation, the angle that the neutral axis makes depends on the applied force. This is a bit counterintuitive, but this is a good takeaway from the derivations that we have done. Okay, So the other important point that I wish to say here is, what is this sigma z? So sigma z is the direct stress or normal stress. Now we have expressed sigma z in terms of the applied, so I made a mistake here. So this is my. Okay, now you can see that the direct stress or normal stress on the cross section is a function of x and y. Okay, you can see from this expression that it is a function of x and y. So sigma z is going to vary at different location on the cross section. Now what is our primary objective? The primary objective is to find out the maximum normal stress that is developed in a cross section due to the applied moment. Okay, and how do we find out the maximum normal stress? It is quite impractical to find out the normal stress at every point on the cross section, and from there to find out the maximum value of the normal stress. So what in practice is done is that, from our understanding of the geometry of the cross section, we figure out certain points which could be the probable location of the maximum normal stress, and we find out the normal stresses from this expression at those probable points. And after we do that, then out of all those values of normal stresses, we see by trial and error, we see which one is having the maximum value, and that is the location of the maximum value of the normal stress, and we get the maximum value of the normal stress. Now the next job is to see that this value of the normal stress, maximum value of the normal stress, is less than the allowable stress of the material. If the maximum normal stress that is developed in a section is more than the allowable tensile or compressive stress of the material, then we have to redesign the entire cross section so as to bring down the maximum stress below the allowable stress. Okay, that is the primary objective of this entire analysis. But nonetheless, you can that is one objective of this analysis. The other objective, of course, there would be certain weaker location of a cross section, and you might need to find out the stress that develop at that particular location of the cross section and see whether it is below the allowable stress of that particular location. Okay. So with this, I will end this lecture. In the next lecture, we will solve certain numerical example to see how to implement the theory that we have learned in this lecture for solving problems. Thank you.